Hello again, and welcome back to this tutorial series. This is lesson number 6, and the series name is an unknown. But anyway, I've given at least this, I've given this lesson a name, and I've called, I hope I have anyway, this lesson, Teaching a Dummy for Dummies. Get it? For dummies thing. Anyway, I'll probably get in trouble with the For Dummies publishing company, but so be it. Anyway, the question being asked at the end of the last tutorial was, how do we teach the stupid computer how to subtract? And I put that question hypothetically to a hypothetical smart teacher. How would they go about doing it? Because our smart teacher gave us a rule. You recall that rule that if we have A and B, and we're trying to do this, and the rule was, if B is bigger than A, flip. Remember, you flipped proceed, then so that's actually 2 steps there. Step 1, step 2, and the final, let's do as normal, and then put a minus sign in front of the result. Make result negative. Okay. Well, the problem is with the computer is we're stuck at the first step. But at this point, anyway, I'm going to assume that the computer hasn't any circuitry in it in order to make this comparison. And there's a reason why I'm making an assumption. In fact, as it turns out, we'll find out later, the way a processor figures this out, if B is bigger than A, actually uses subtraction. That is, it subtracts the two, and depending on the outcome of the subtraction, it can then tell you which one is bigger. So in fact, it can't use this test to determine how to subtract, because this test relies on subtraction. It has to do with subtraction to determine which one's bigger. So it's no good for a computer. Alright. So, what's he gonna do? Or she? Our teacher that has to stop being a teacher who tries to make you understand. That's what a teacher is. Gives understanding. And instead become an instructor. And what's an instructor? I don't know what the dictionary says, but I'm going to give a definition of an instructor. Did I spell it right? No. Too many answers. Instructor doesn't care if you understand. Instructor assumes you are an idiot. That's one thing. Won't answer any questions. Tells you what to do. It doesn't explain. Okay, and that's exactly what we need in order to teach, so to speak, a computer how to do subtraction. Now I've come up with an instructor, an algorithm that, algorithm, I'm going to use a word that you probably know, a step-by-step way to do subtraction that doesn't rely on this comparison. Okay? In fact, it doesn't rely on anything. All you do is you always follow exactly the same steps every single time. And let's say we use the borrowing rule. So our example was 7 minus 8. There it is. Okay. The instructor is not going to answer any questions, so we'll just do exactly what we've been told to do. We borrow, and that gives us 1 here, and 7 here, and minus 8 here, and who knows what else here. We borrowed 1, but don't know where it came from. To do the subtraction, 17 minus 8 is 9. Great! I've done, tell the teacher, I've done my problem. I did 7 minus 8, the answer is 9. Teacher's gonna get mad. Teacher always gets mad. And the teacher says, no, you're not finished. What's this question mark thing here? Well, that's where I borrowed the 10 from. Okay, so you borrowed 10. I didn't see you put it back anywhere. Well, I can't put it back. I don't know where it came from. Just put it back, and you'll be done with the problem. And I'm going to tell you exactly how to put it back. All you do for your next step, if you don't know where that 10 came from, it magically came into existence, to give it back, since in a sense we have subtracted 10 from a result. So to put it back, we got to add it back. So we add 10 and subtract from that the result that we already have. We're just being told to do this. We don't know why. Subtract. And that gives us a result. And the last step is to multiply the result by minus 1. And the answer is minus 1. Okay? Well, that works. We didn't have to compare anything. We followed all the rules as normal, except when we noticed a question mark, something we borrowed, the rule is to take what we borrowed, subtract the answer we already have, and then multiply by minus 1. Now that's actually completely different from the other algorithm, because we didn't have to compare anything. And notice that everything is in positive. At no point are we subtracting a big thing from a little thing. What we've done is we've automated the process of comparing if A is bigger than B. That now is automatic. It's been done. And if you work this out slowly with letters and symbols and stuff, what you're going to find out is that this here 10 that I've added in here actually cancels with this 10. This is like a negative 10. So those cancel. And then what's happened here is the 8 and the 7, the 8 and the 7 got reversed. So the process of reversing this is also automated. In fact, it works out, try it on your own. It works out that this whole thing amounts to the following. A minus B equals A plus minus 1 times B. And that's what you learn in university when you study the mechanics behind algebra. You learn that subtraction is a fiction. All there is adding. And this times minus 1 is what's called taking the inverse of B. So A minus B really means A plus the inverse of B. And what I've come up with here is a very, very complicated way of doing this. Unfortunately, though, however, the last step and the step here involves multiplication. And that's a very, we're trying to do subtraction, and here we've gone and introduced our multiplication. Well, that's one problem. And the second problem is, what's minus 1? You haven't figured that out yet either. So there are two problems with this. It's algorithmic, in which there's no thinking. That's good. So we have two problems. It involves a multiplication, which is slow. And that's problem number 1. And problem number 2, what the heck is minus 1? Is how do we take the inverse of a number in the Intel X8086 line? Well, it turns out that both of these problems have a very simple solution. They can be solved very, very easily. And I'm going to tell you right now. I guess I might as well just tell you how to do it, because it's so easy. I can tell you in 2 lines. In fact, we don't need to know part 2. When I tell you how to do this, how to multiply by minus 1 without even knowing what minus 1 is, we can then work out what the number minus 1 actually is. Here's the rule. And this can be done very, very quickly. Comparison, I showed you before, could take a long, long time. If someone were to design a comparison circuit, take this. This is a bit of a diversion, but take this example. I'm making this up on the fly. Okay, here's one number, here's another number. Which one's bigger? Well, what you would have to do in order to determine the bigger of the two is start from left to right. And if you're lucky, you're going to hit a 1 on one of these guys first, and then you can say, okay, that's bigger. But if you're unlucky, like in this case, everything's matching, so you keep going and keep going. And in the worst case scenario, or nearly worst case scenario, you have to scan through every single bit and make a comparison, a bit comparison, which we haven't designed yet, and find out when we hit a 1 on one of them and a 0 on the other, then the one that has the 1 is bigger. So that is slow. We don't want that. And of course we don't want multiplication. But here goes. How to multiply by minus 1. This, okay, I won't ask the question. Most people, when I think, how are you going to represent a negative number on a computer and a limited number of bits, they just will tell you, okay, make the top bit, if the top bit's 1, it's negative, etc. This is negative, and if the top bit is 0, then it's positive, and do everything else the same. That's not the way it's done, and there's a definite reason for that, and I'll leave that as a puzzle for you. That's the way a human being might think about negative numbers, like that this is just a minus sign. But the computer does not like that way of doing things. And here, when I tell you how to multiply by minus 1, you'll see why. So it's a two-step process. First, flip all the bits. That's the first part. Second part, add 1. If you do that, you will end up with the negative of any given number. Okay, well, let's try. I have an example here. I'll just use my example to save time. That in hex is 5AC5. And the other number is which is 375D. Work that out. Now, suppose this is from AX and this is BX. And we want to do subtract BX AX. According to the rule, what we do is multiply AX by minus 1 and add. So what is the negative of AX? Flip the bits. There goes the flipping. 0, 1, 0, 1, 0, 0, 1, 1. No, not too far. 1, 0, 1, 0. Then 0, 1, 0, 1. Then 0, 0, 1, 1. And then 1, 0, 1, 0. And then we got to add 1. And that is minus AX. If you work that out, that is A53B. Okay? So bx minus ax, and now I have to go back to our computer. This guy. No, let's see again. bx is 375d. And ax is 5ac5. Right? Okay. And what we want to do is subtract ax from bx. So we want to take this away from this. But instead of doing it that way, what I'm going to do is add the negative of ax to bx. And that should give the same answer. So let's try that. Add to bx. I can just put the number in. A5 3b. Alright. Okay. Trace through that. DC98. So the answer DC98. Now let's try it using the subtraction instruction. Lost bx, put it back. And 37.2. Okay. The instructions are already there for me. But is that where I am? Yeah. So subtract from ax. Yeah, no, we don't want that. We want to subtract from bx ax. That's what we want. Okay. Now that should give us the same result. Let's try it. There it is, DC98, same as before. So now we figured out a way to determine the negative of a number. And this subtraction, you can guess what has happened in this, is it probably did exactly what we did. It flipped all the bits, did an addition, added one to the result, and it gave us that, which is the answer that we expected. The other way to do it, like teacher one way to do it, but bx should have stored bx somewhere. The intelligent way would have been to subtract from ax bx and then apply the -1 thing on that line. Okay. So the subtraction, the positive subtraction of ax minus bx is 2368. So it turns out that ax minus bx equals 2368. Now, in theory, this, if we flip all the bits of this and add 1, we should get this number. Let's see if it works. 2, 3, 6, 6, 4, and 2 is 6, and 8 is 8. Let's flip all the bits. Alright, but we're going to add one now. We add one to all the equals here. That makes 8, which equals the top one. That's 4. 8 plus 4 plus 1. 8 and 4 is 12, plus 1 is 13, which is a D. Here we have 8 plus 4, which is 12, which is 1 less than 13, which is C. This is 8 plus 1, which is 9, and this is an 8. So this is, in fact, the negative of that. So you can see all this stuff works. And now we've taught a dumb computer how to do a subtraction. And now we can answer the question, what is minus 1? All we've got to do is take 1, flip all the bits and add 1. So we get minus 1. That's plus 1. So minus 1 is the same as FFF. So we didn't need to invent minus 1. We needed to invent a way to generate minus 1, and then we generated it. And this is pretty clear that if I add 1, get rid of the plus. If I add 1 to this, I'm going to get 0. 1 plus 1, put this thing here. 1 plus 1 is 10, because I carry. 1 plus 1 is 10, and I carry. And it keeps going on with those carries. The carries are cascading along and canceling out all these 1s. The only thing, so here are all the carries. There's an extra little 1 here that pops out for 5. And that there is called a carry bit. In fact, it has a special name, special meaning. We call this the carry bit. And if you notice here, that bit is represented when we do certain operations at the end here. It's one of these flags. One spills over, or actually if a 1 gets tossed out to the left or the right, this bit gets set. It's telling us that there was a carry that had nowhere to go. So there's a meaning to this extra bit. Even though it's not part of the result, it can be used for testing things. And that's how the computer, that's the way that the processor uses subtraction in order to determine bigger or smaller. In fact, there's an instruction called JC. Give it a number. This instruction says is what they call a conditional jump. The jump means to change the location of this instruction pointer. if the carry flag is set, jump to 102. Okay, now that instruction is just part of the Intel instruction set. But watch how the debug program interprets this jump if carry instruction. Type R. It doesn't say jump if carry. It says JB. And what this B stands for is below. This says jump if below. So it uses the carry flag as a way of determining if something was less than or greater than something else. But yeah, that's probably too much detail to go into. But you can see so that there's something going on with this carry flag that it's not necessary for you to know about. Anyway, that's all I wanted to go over for this bit. And the next, now I've talked about subtraction and division. The next time what I want to do is look at addition, because now we've seen that subtraction and addition are the same. So how can we add numbers using the circuitry in the computer? And I don't like to look things up because for me it's more fun to try to figure it out. And I used a few things that I knew that would already have been built into the processor, and built a little adding machine, and hopefully it works. And next time I'll show you my adding machine, and that's probably wrong, but anyway, we'll look at it, and if it is wrong, maybe we can figure out how to fix it. Anyway, thanks for watching. See you next time.